All right, so we've got an indirect contact heat exchanger. We've got air flowing through the shell part of it and R134A, the refrigerant, flowing through the tube part of it. And we're given some inlet and outlet conditions for the air and for the R134A. We've put this on our diagram. We're supposed to find the mass flow rate of the refrigerant, and then we're also supposed to find the heat transfer rate between the air and the refrigerant. The assumptions that we'll make for this problem are the typical ones that we will make for a heat exchanger. Steady state, power is equal to 0, no kinetic and potential energy changes. And then if we consider the entire heat exchanger, we assume that there is negligible heat transfer between the heat exchanger and the surroundings. So first things first, we want to find the mass flow rate of the refrigerant. So I'm going to apply my conservation of mass for both the air and the R134A. So since it's steady state, the dm/dt goes away, and I've got the sum of the m dots going in equals the sum of the m dots going out. So for the shell, m dot 1 is equal to m dot 2, and that's just m dot of the air. And for the tube, m dot 3 is equal to m dot 4, which is just the m dot of the refrigerant. So with that information, now I'm going to apply the conservation of energy. I'm going to make the assumptions that I typically do, and first of all, I am going to make sure that I'm talking about, I know what boundary I'm talking about. So you see here that I've drawn in my red dotted line, and so if I've drawn my system boundary like that, there's no heat transfer crossing that system boundary, so everything's going to go away except the sum of the m dot h's in and out. So going in, I've got things going in at 1 and at 3, and things going out at 2 and 4. And then I replace the 1, 2, 3, and 4 with refrigerant, REF, and air. And I got that from my conservation of mass. And then I just rearrange to get all my like terms together. And then I solve for the mass flow rate of the refrigerant. So I can figure out for the air, I can figure out my H values by looking up the H value at T1 and P1. So T1 is 32 degrees or 305 Kelvin. I could do the same thing for T2, 22 degrees or 295 Kelvin and get my H value there. And then for the refrigerant, I need to look at my tables for R134A. So this is A11, table A11, and all I've done is I've looked so at state 3, I've got a quality of 2, my pressure is 5 bar, and so the only thing I need to do is look in those saturated tables that are organized by pressure and use the H sub F and H sub FG value to calculate what H3 is. For H4, I know that my pressure is 5 bar and my temperature is 20 degrees Celsius. So if I look at 5 bar, if I look at my saturated tables, at 5 bar my saturation temperature is 15.74 degrees Celsius, which means that since my temperature, 20 degrees Celsius, is higher than the saturation temperature at 5 bar, then I have to be superheated. So I go to my superheated tables at 5 bar and 20 degrees Celsius, and I just pull off the corresponding H value for that. So I've done that. Now I've got everything, all my H values. The only thing that I don't actually have is m dot of my air. I am given the volumetric flow rate, and since the mass flow rate of the air in is equal to the mass flow rate of the air out, I can use the volumetric flow rate at state 1 or state 2 to calculate what m dot of the air is. However, I only know v dot of the air at state 1, and that's the 50 meters cubed per minute. So with that information, I just need to plug that in. The specific volume of the air at state 1, I can't look that up, but I can calculate it using my ideal gas law if I made the assumption that air behaves as an ideal gas, which would be perfectly okay here. And so RT1 over P, I do need to make sure that I calculate the specific gas constant, which is R bar over my molar mass. And that molar mass you can look up in table A1. And I get 0.287. So when I plug things in, make sure you plug the temperature in as Kelvin, I get 3.775 kilograms per minute. So I probably should put that I assume the air behaves as an ideal gas in my assumptions, but I didn't, but just pretend it's there. Okay, and then I'm supposed to find the heat transfer rate between the air and the refrigerant. So the way that I'm going to do that is I'm going to draw my system boundary so that heat transfer does cross that system boundary. So I could do that by just looking at the refrigerant, drawing my control volume around the refrigerant, or just around the air. So everything in that heat exchanger with the exception of the tube, the refrigerant going through the tube. So let's do it both ways. We're going to do it around the refrigerant only, and we'll apply our conservation of energy. Of course, all these things go away except the Q dot and the M dot H's. My Q dot doesn't go away because now the way that I've got my system boundary drawn, I do have heat transfer between the refrigerant and the air. And because I know the M dot of my refrigerant and the H value, H3 and H4, I already calculated that in part A, I can get my heat transfer rate of 574 kilojoules per minute. And it's a positive number, which indicates that the heat transfer is going into the refrigerant from the air. Now let's do it the other way. If we draw our control volume around the air and we apply our conservation of energy, we've got Q dot, because yes, we do have Q dot, equals the sum of the M dot H's going out minus the sum of the M dot H's going in. And the M dot in and out of that control volume is the M dot of the air. And I've got all the information needed from part A to plug in here, and I can get negative 574 kilojoules per minute. So what you notice is that Q dot, if I draw it around the refrigerant, it's a positive number. If I draw it around the air, it's a negative number. So the magnitude of both of those numbers should be the same. It's the negative or the positive sign that tells you which direction it's going. So I can tell based on that positive and negative sign that the heat transfer is going from the air into the refrigerant. All right, well, I hope that was helpful. Let me know if you have any questions, and thank you for watching.